Start streaming. Hello everyone, my name's Guy Davidson, and I'm going to talk to you about portable floating point calculations. I'm the former head of engineering at engineering practice at Creative Assembly, which are owned by Sega. But right now, I'm the head of engineering at 6 Impossible Things Before Breakfast. We're still in stealth mode, but you'll hear about us soon. We're working on a game engine. I am the chair of programming languages for the British Standards Institute. The UK is a monarchy, so I like to style myself as the king of programming. You all need to learn how to bow now. I'm an ISO C++ global expert, which is a lot more exciting than it sounds. And I'm also a member of the C++ committee. We're meeting in Wrocław, I hope I've pronounced that correctly, next week. I'm also the chair of the ACCU conference, if anyone feels like now is the time to start your speaking career. We're always looking for new speakers. And 2 things I should tell you. Every speaker has stage fright, and every speaker has imposter syndrome. So don't let that put you off. It's just a thing you've just got to deal with. There we are. I'm the game dev track chair at CPPCon. I'm a regular speaker in Europe, and I play the piano, and I sing first bass for the Brighton Festival chorus. I run a film club, I grow my community, I do all sorts of things. I do not like to let the grass grow under my feet. For example, during lockdown, I wrote a book with Kate. You should try it. You should try writing a book. It's fun. Has anyone bought this book? Wow. Has anyone read this book? Let the record show that 85% of the audience have bought and read the book. Nearly 96, actually. Yeah, if you find Kate, go and say hi and tell her you enjoyed the book as well, if you did enjoy it. Did anyone enjoy the book? Great. Good. Okay, you should certainly buy it. There's a nice offer for you if you want to take a photo of that. But you've all bought it, so you don't need to take that photograph. Right, here's our agenda. Stop me to speak up or slow down and take notes. Tell me where I can improve the talk. This is the first time I've given this talk to a C++ engineering audience, so I'm a little nervous. But we're going to talk about non-integral values, standardizing non-integral arithmetic, standardizing C++ for non-integral values, and improving reproducibility of non-integral values. That's where the fun stuff is, I expect. So non-integral values, let's start with our arithmetic operations. Who's heard of plus, minus, multiply, and divide? Everyone? Good. And each of the inverse functions, subtract and divide, can create results that take you outside of the original domain. So for example, addition on natural numbers stays in natural numbers, but subtraction takes you to the integers. Multiplication on the integers keeps you in the integers, but division can take you into rational numbers, and rational numbers are ratios. The clue is in the name. They are countably infinite, which is just beguilingly interesting, and half of the rational numbers lie between 0 and 1, or between -1 and 1, actually, I suppose, if we're talking about negative numbers. They're very analog things. They're quite delightful. Every 2 rational numbers has another rational number between them, and they are reducible via the fundamental theorem of arithmetic, which talks about prime factorization. So if you have 2 over 4, you can say, well, we can eliminate 2 and have 1 over 2. That's great, and it makes the numbers smaller. Anyone here used a slide rule? Yes, of course, Fran and Steve have. Yep, good. Go and buy a slide rule. Learn how to use it. It's fun. It's revealing. It will reveal a lot to you about the nature of the universe. I'm rather fond of slide rules. I'm also rather fond of rational numbers. There is something of the cosmos about them until you want to add them. Yeah, exactly. See, multiplying rational numbers, that's easy. You multiply the numerator and the denominator, and the job's a good one. But when you have to add, you've got all this cross-multiplying to do, and things blow up really quickly. They get out of hand. It doesn't take too long to overflow your domain, and all hell breaks loose. You can, of course, reduce them by factorizing, but it's actually quite rare that you'll find all your prime factors and you'll make your number small, and you know, that's not good because people need to know how long these things will take. You might decide, well, I'll use an arbitrary sized integer class for my denominator and my numerator, and then you've got a memory problem as things get larger, and it's just a long problem. You can't just say, well, that depends, when asked how long something will take. Clients don't like that. Now, we came up with a solution quite a while ago. Well, I say we, people in history did. And it depends on who you ask exactly when, because decimal fractions, which is what we're all used to, they've been in use for quite a while, several thousand years, in fact. Common representation is a different matter. Who's heard of John Napier? Okay, John Napier, person you should all know. He wrote a book on constructing tables of logarithms at the beginning of the 17th century. And he used a decimal point there. Now, the decimal point tells us that we are now approximating via sums of powers. So the first digit after the decimal point gives us a number of tenths, and then the next one gives us a number of hundredths, thousandths, and so on. And by adding more and more negative powers of 10, we can improve the precision of the number that we're at. But there are only a small set of numbers which can be represented exactly. Because since we are in base 10, ordinarily, and the prime factors of 10 are 2 and 5, as I'm sure you're all aware, the only rational numbers that can be represented exactly are those whose denominator is representable as a product of powers of 2 and 5. So, for example, 1/8, 0.125, prime factors of 2, 125 thousandths. 3/40ths, that's 5 times 8, so that's 75 thousandths. But other numbers aren't so lucky. In fact, most numbers are not so lucky. Here's 1/7, 0.142857 recurring. Now, I did that by hand. And the reason I did it by hand is because I asked Clang, what's 1/7? And it gave me this. So it's fine, 1.42857, 1.42857, 1.4284921269281, and off we go, far, far away from reality. Well, I say far away, we're into, 10 to the negative 12 there, but, billionths are important. And this inexactitude might spell doom for engineering, but empirically it doesn't. Here we are in a building. Has this building fallen down about our ears? Is this all a synthetic? No, it hasn't. We're fine. It's good enough. So how do we manage this? So, right, what's the size of the observable universe? Fabio? Yes, you do. I'll bet you do. No? All right. Anyone else would like to hazard a guess? The size of the observable... All right. It's 8.8 times 10 to the power 26 meters. That's a big number. But look at that exponent, 26 decimal places. That gives you the width of the universe to the nearest meter. 36 decimal places will get you the width of the universe to the nearest atom. And they're quite small. So, 26 decimal places is quite ludicrous. Really, we can get by with far fewer. It'll do. Errors will propagate, but there are ways around that. There's all sorts of things that we can do. But computers are binary creatures with no notion of fractional parts. So how do we resolve this? All right, what's this value? Now, you might tell me, oh, that's obviously 26,998. And you'll be completely wrong. Well, not completely. If you assume that this is an integer, then yes, it is 26,998. But what I haven't told you is that the lowest 4 bits are reserved for negative powers of 2. So the value is actually 1,687.375. Okay. And adding and subtracting is simple enough. We don't compare powers in those operations. We simply add the numbers, the powers carry, everything's lovely. Multiplication is a little bit harder. If you pass these bit patterns to the multiplier, you'll get this, 288. And as you can see, that is not 18. To get the expected value, you have to right shift by 4 bits. And this tells you straight away that there is some overhead for working in fixed point arithmetic. Since fixed point arithmetic isn't natively supported by C++, you've got to manually write a fixed point class. And there are some CPU intrinsics available on some processors. But that final part of the operation, where you shift the result, that highlights another problem, because precision will fall away with each calculation. Now, simulations, I work in games, I write simulations, and they typically make heavy use of Newton's laws of motion, and that involves a lot of multiplication. And it won't take long for your model to diverge noticeably from user expectation. And the problem we have is that the binary point is fixed at bit 4. And that means we have to divide by 16 after every multiplication. And if we wanted more precision, we would have to divide by even greater numbers. That would yield an even greater loss of precision. And in the prior example, if we simply left the value alone and shifted the binary point to the left after each multiplication, there'd be no loss of error. So maybe there's a solution, but we'd soon run out of magnitude. It's just not very nice. So let's look at another representation of numbers. Now, in the first line, we're performing addition. So 3 decimal places in each number are used, but the second number has a higher magnitude. But look at the results. The result of the addition has 4 decimal places, and the result of the multiplication has 5 decimal places. We can accommodate the expansion of precision rather more easily than with fixed-point arithmetic. And rather than keep the decimal point in the same place in the number, we're storing the number in 2 parts, a value and a magnitude. So the value part is known as the mantissa, or the significand. That's the modern name, apparently. People stopped saying mantissa about 40 years ago. Nobody told me, but there we are. Well, the magnitude part is known as the exponent. But note what's happening to the mantissa, though. It's getting longer. And if you're working to 4 significant figures, then you have to decide what to do with the remaining figures. You could truncate the value, you could round it to the nearest value, but after every individual operation, you have to round the value to fit. And this is a tricky problem which will return to bite us later. So let's try something in binary. Now, we have to make some decisions. Which part is the exponent? Which part is the mantissa? I'm going to choose the bottom 6 bits for the exponent and the top 10 bits for the mantissa. And this gives us that. So let's unpack this. When we were in base 10, our mantissas lay between 0 and 10. For this example, I have decided that our mantissa lays between 0 and 1. So looking at the leftmost 10 bits, counting left to right, observe the color coding here. We've got 1/4 plus 1/64 plus 1/512 plus 1/1024, whilst the rightmost 6 bits total 11. And this gives us an exponent of 2 to the 11th power, which is, of course, 2048. And this evaluates to 550, and a similar approach to the second value evaluates to 0.2890625. Now, we have a problem, though, because looking at the representations, we have this, and multiplying those 2 representations using standard integer arithmetic won't do the job. So it kind of worked in fixed point, and you had to do some correction, but we have nothing for this. The process of floating point multiplication is actually quite a task. And additionally, the schema that I proposed does not invite a unique representation for each number. So, for example, the value on the right has multiplied the mantissa by 4. And it has divided the exponent by 2 to the power 2. And how does one represent negative numbers or negative powers? This is just not good enough. And it would cost a single bit of resolution for the exponent and the mantissa to add sign here. And another problem is interoperability. How do you tell your clients how wide the exponent and the mantissa is? Is? English is my first language, believe it or not. What if you're exporting a library to some anonymous third party? How do you identify your choice of rounding algorithm? There's plenty of room for error, which sounds like a job for standardization. So IEEE 754 is what you're looking for. Who has heard of IEEE 754? Thank the Lord for that. Great. Okay, good. So about half of you. And this standard was first published in 1985. It's undergone some revisions since then. And the C++ standard refers normatively to document ISO/IEC/IEEE 60559:2020. So this is ISO importing a third-party standard into its ecosystem. Gives it a new name, completely eliminates the identity with the exception of the IEEE. So it's basically the same thing as the latest revision of 754. And you don't need to read this standard. It's worth it, but you don't need to read it. You can simply rely on your vendor implementation to be conformant. This is my straight face. Anyone play Rome Total War ever? Anyone play any Total War games? Okay. Now, I've given this talk to some game conferences, and everybody went, yeah, it's great. So I'll explain what's going on here. So we wrote this in 2001. We started this in 2001. It took about 2.5 years to come out. It was quite large. But the idea is it's It's a battlefield with thousands of individual characters on it, and you can play multiplayer, you can play against each other. And there are many megabytes of state, and the idea of squirting that around the internet at 10 hertz back in 2004 was nonsensical. People were still using dial-up. Anyone here use dial-up? Oh, quite a lot of you. Wow, you poor people. Germany, thank you. Right, okay. Land of technological advancement. So we couldn't transmit the change of state from tick to tick. The only thing that we could do was transmit the commands that were issued to the simulation and then update every agent playing. And this was a surprisingly tricky problem because it meant that it's very easy to write code that's not deterministic. You know, you might forget to fully initialize an object, so you'd be left with whatever was on the stack last time. You might pass a reference to an object which is actually not part of the simulation, it's part of the view or the camera, and so that changes things, and it's very unpleasant. But we devised programming guidelines and debugging strategies, and we locked it all down, and it served us well for 2 decades. We got deterministic multiplayer working for the same binary on different computers. And it continues to work to the best of my knowledge. I've been out of CA now for a little over a year. But Sega are very keen to see a console version. They'd love to see a console version of Total War, so that Xbox and PlayStation and even Switch players can join the fun with PC players. And it would be quite feasible to have Switch players competing against one another, or Xbox players, but nobody wants a fragmented audience. You want everyone playing Total War to play against everyone else in one happy world. You should be able to connect to a lobby and just play with anyone at all. That's how it should work. And you know, if you're into games, you might have heard of crossplay. Crossplay is quite limited. We need something more than that. Well, you might ask yourself, why won't the same code work the same way and yield the same results on different platforms? Because 2 plus 2 is always 4, isn't it? That's not a trick question. 2 plus 2 is always 4. Pardon?
Depends on what.
Well, yes, all right then. Or if you're working in base 3, then anyway. But you all know about the butterfly effect. Once something goes wrong, it just propagates. So it's Godbolt time. Right, I'm going to do this. This is going to work. Oh yeah, it does. Wow, look at that. Except it's completely illegible, isn't it? Who can read that number? Okay, who can read that number? Right, I'm going to explain what's going on here. And when we go back to the other screen, the link will be up there and you can take note of it if you're really interested. But what's going on here is we have a piece of code up here. I'm going to point to the screen. Right, got a piece of code up here. It's working through the NVIDIA compiler. David Olson. Yep, that's yours, isn't it?
Yes.
Yeah, so we have an expert in here, which is why I'm so nervous, but there we are. He's a proper expert. I'm just a learner. And then we have Clang, and we're working at particular values. And the real problem is, as soon as we get to our first calculation up here, where we're calculating distance, on one compiler, the last digit is 7. On another compiler, the last digit is 9. And by the time we get to the end here, proj vector y, on one compiler, the last digit is 8, and another compiler, the last digit is 9. Although the other values, here are all the bit patterns for the values, they actually do all match. And this is really quite annoying. It's a real problem, you know, and I want to focus on reproducibility across implementations. This works, this is brilliant. Right, take a picture of that if you want, or ask me for it later. I'll be delivering the slides to Jens. Cameras, right, I'll just... Oh, this is gratifying that you're also interested in a random piece of Godbolt code. Right. Let's talk about standardizing non-integral arithmetic. So thank heavens, the IEEE decided to standardize floating point arithmetic back in 1985. The International Electrotechnical Committee thought, wow, we'll have that. And they published it in 1989. And then the British Standards Institute, for whom I work, they adopted it in 1990. And then IEEE went and revised it in 2008. So ISO said, right, we'll have some of that as well. And they introduced 60559:2011. And then IEEE revised it again in 2019. And this is what we have now, 60559:2020. So what I'm going to do, I'm going to rush you through this, just give you just an overview. But I do recommend that you find a copy for yourself, and devote, it's about a 4-hour read. It's a well-written document. It's a 4-hour read. It's 2 glasses of wine and a rainy Sunday afternoon. That's how I did it. It's perfect. Now I'm going to stay current and focus on the latest version. So the standard specifies formats for binary and decimal floating point data for computation and data interchange, addition, subtraction, multiplication, division, fuse, multiply, add, square root, compare, and other operations. Conversions, and then floating point exceptions and their handling, including data that are not numbers, like infinity and not a number. Great name. Who says naming's hard? Honestly, we've got this value here. It's not a number. What should we call it? Not a number. Brilliant. Genius. I'm going to do some foreshadowing. Yes, plenty of you nodding away. I'm also going to highlight parts that aren't actually relevant to portability, necessarily. There we are. So it opens with a section on definitions, abbreviations, and acronyms, and there's more foreshadowing. So this is fairly mundane. Language defined means behaviour that's defined by a programming language standard supporting this standard, like C++. That's a programming language that supports this standard, or does it? We'll get back to that. However, this is not so mundane. Behaviour defined by a specific implementation of a specific programming environment conforming to this standard. So this tells us that there are bits of the standard, of the 754 standard, which has latitude amongst implementers for a particular language. Right, onto the meat of the standard. You probably, if you're used to floating point, you might be familiar with this. 1 bit for the sign, 8 bits for the exponent, 23 bits for the mantissa. This is the binary 32 standard. And this is the binary 64, where everything's just a bit bigger, except for the sign bit. The choice of which of this standard's formats to support is language defined, or if the relevant language standard is silent or defers to the implementation defined. The names used for formats in this standard are not necessarily those used in programming environments. So IEEE 754 calls them binary 32 and binary 64. We know them as float and double in the general case. So the standard goes on to tell us what I said earlier, that floating point arithmetic can only represent a finite subset of the continuum of real numbers. Consequently, certain properties of real arithmetic, such as associativity of addition, do not always hold for floating point arithmetic, so order of evaluation matters. That's clause 3. There are 11 clauses. Clause 4 deals with attributes and rounding, so attributes are associated with the program block. They use different language here. This is a specification for all languages. Maybe we don't have program blocks in some implementations, but it's attributes. They're for a region of code. There are 2 kinds of attributes. Some change the operation of functions, and some are implicit parameters. Rounding falls into this category, and there are 5 rounding modes. I won't go into them. You can look this up. Rounding's a beast, though. So during the production of Rome Total War, as we were trying to achieve determinism, we would find desynchronization would occur on machines with different graphics cards. And it turned out that one graphics card driver preferred a different rounding mode. But this is just for rendering, so it shouldn't affect the simulation. It changed the rounding mode while executing the driver code and didn't change it back. I was so angry. Anyway, clause 5 is where things get meaty. We have nearly a quarter of the document devoted to this. We've got rounding functions particularly. Next and previous functions, log functions, all the arithmetic operations, which includes the usual arithmetic, and square root, and fused multiply add. There's that one again. And this is where things become problematic, because FMA computes x times y plus z, rounding only once to the destination format. And this differs from a multiplication followed by an addition, because that will round twice. And I've already mentioned the butterfly effect. Got 2 roundings rather than 1 rounding. So divergent results, potentially. Of course, some results will always, you'll get the same value. A half times a quarter plus 3/8 will always evaluate the same way, whether or not you use FMA or A times B plus C. But sometimes is a bad word in deterministic evaluation. It has to be universal. The problem here is that compilers are free to choose how to implement the expression. They can reorder within an expression statement as appropriate for the optimization chosen on the command line. Now, you might think, well, okay, can I just have individual expressions followed by a semicolon, so not have these chains of expressions. But it's just horrible. It doesn't really work. One of the things I like about using C++ is that I've got operator overloading. I can do things like this. And there's a truckload more stuff going on here. There's conversion operators, sign querying, negation, different types of rounding, ordering, comparison. I might do a full walkthrough of the standard if everyone really wants to see it. Is anyone familiar with the Goldberg paper? So the Goldberg paper is what every programmer should know about floating point arithmetic. If you just query Goldberg floating point arithmetic, it's a big paper. It'll take you longer to read than the standard, but they're both worth reading. But let's rush on. So infinity, that's a remarkably simple concept for as far as the standard is concerned. You do anything with infinity, you get infinity. It's also signed because obviously infinity is signed. Nans, on the other hand, are really quite subtle. You can use them for uninitialized objects, you can loudly signal invalid operations, or you can quietly signal exceeding range, or generally identifying that something has gone wrong. And nans propagate, just like infinity. Once your program has gone wrong, it cannot be recovered with valid data. Nan takes advantage of representation rules, because not every bit pattern actually represents a number. It's an interesting field. You can look into that yourself. The sign bit might seem trivial, but there are some interesting edge cases. How do you choose the sign of 0? Right, clause 7 talks about exceptions, what can cause an exception, invalid operations. That's what causes them. So things like the square root of a negative number. And there are some things you can't do with infinity. You can't multiply 0 by infinity, and you can't divide infinity by infinity. Those are invalid operations. Division by 0 gets its own exception. So does overflow, where a result can't be represented by its target type. So does underflow. This happens when a result is smaller in magnitude than can be represented. So you've got something really close to 0, much smaller than the minimum representable value of your floating point type. Inexact is a handy one, and this happens if no other exception is raised, and the result differs from what would have been computed if you had, unbounded infinite precision available to you. So this happens, most of the time. You'll get an inexact exception. Clause 8 also talks about exceptions. Clause 9 describes some extra nice-to-have operations in your conforming standard, like trig functions. So we've got 2 more clauses to go. Next is clause 10. Things get interesting here, because in clause 5 we looked at how to perform a single operation. And clause 10 opens with a summary of clause 5. Clause 5 of this standard specifies the result of a single arithmetic operation. Every operation has an explicit or implicit destination. For numerical results, one rounding occurs to fit the exact result into a destination format, one rounding. And that result is reproducible in that the same operation, applied to the same operands, under the same attributes, produces the same result on all conforming implementations in all languages. And that is a bold statement. All conforming implementations in all languages, job done. Now, language standards define syntax for expressions that combine multiple operations. But as we saw, we have A times B plus C times D. By the way, that X is actually the Unicode multiply. It's not an asterisk, it's the Unicode multiply symbol. And I encourage you all, in all your slides in future, to find it and use it. Asterisk is this awful C++ bastardization from when we had, when we only had like 40 keys on our keyboard or something like that. Anyway, a rule for expression, it bothers me. A rule for expression evaluation encompasses the order of evaluation and the formats of implicit intermediate results and when assignments to explicit destinations round once and when twice. Now, the final clause, clause 11, was added to the first revision of the standard in 2008, and it is entitled Reproducible Floating Point Results. Fantastic. And it's the shortest clause in the standard, and it's tempting to read it out in its entirety, but I won't. But I'll summarize. It describes what the reproducible operations are, which is basically all the ones that do something to inputs legally. It describes a reproducible status flag and a reproducible format. But significantly, it defines a reproducible attribute, which is an attribute that is required by a language standard in all implementations. And the clause goes on to say, any conforming language standard supporting reproducible programming shall support the reproducible results attribute, support a reproducible format by providing all the reproducible operations for that format, and provide means to explicitly or implicitly specify any sequence of reproducible operations on reproducible formats supported by that language. So basically, This clause says, and here's how we get reproducible arithmetic that's consistent and identical on all platforms. And it shall also explicitly define a whole bunch of things, including a reproducible results attribute, which indicates when reproducible results are required and when they are not. The final part of the normative standard instructs users how to obtain the same floating point numerical and reproducible status flag results on all platforms supporting such a language standard. It's a list of programming guidelines, 9 do's and 5 don'ts. No, 5 do's and 9 don'ts. And this might come as a bit of a surprise, because after all, typically implementations are 60559 compliant, aren't they? But that means that specifying the reproducible attribute in code should be all we need to get what we want: portable, reproducible floating point operations. Why has nobody told me about this yet? Was the first thing I thought when I read the standard. So let's see how the standard does specify floating point behavior. Standardizing C++ for non-integral values. So you might find this is a slightly sarcastic section title. So is anyone here sufficiently familiar with the standard to be able to tell me where floating point behavior is specified, besides David? Go on, David. You wrote this, didn't you?
Revised it.
Yeah, basically.
Where it defines the floating point types, it says the results of operations are implementation defined.
Yep. Yes, it does. Thanks for that. There we are. So we have 3 distinct types: float, double, and long double. They can represent floating point numbers. The type double provides as much precision as float. The type long double provides as much precision as double. So basically they're saying that all your floating point numbers can be represented in incrementally larger types. An implementation may also provide additional types that represent floating point values and define them, and CV-qualified versions thereof, to be extended floating point types. The standard and extended floating point types are collectively termed floating point types. Except as specified in basic.extended.fp, this is this bit here, the object and value representations and accuracy of operations of floating point types are implementation defined. Their compilers can do what the hell they like. They don't care. This is... So I don't know about you, but I felt a sickly panic when I read the object and value representations and accuracy of operations of floating point types are implementation defined. It's weird what gives you nightmares, isn't it? So I went scurrying to basic.extended.fp to see what was on offer. Here we are. Yes, well may you laugh, David. If the implementation supports an extended floating point type, whose properties are specified by the ISO/IEC 60559 floating point interchange format binary 16, then the type def name std floating 16_t is defined in the header std float, and names such a type, the macro std cpp float 16t is defined, and the floating point literal suffixes f16 and f16 are supported. I said the second f a bit louder because it's uppercase. And then it does that for std float 32t, 64t, 128t. And that's all it says. It tells you nothing about operations, nothing about accuracy, rounding, anything at all. It's a start. It's a start. But this is a first bit of conformance with 60559. And at the moment, I don't think there is an implementation out there that actually supports this. I could be wrong. I think GCC is on its way. Thank you. Yeah, I think GCC is on its way. NVIDIA, great. Of course it is. You have a bunch of great experts working on the NVIDIA compiler, don't you? Besides you, obviously. I'm not saying you're not an expert. You are. But, people of your caliber are there. Yeah. But anyway, this is not much help for our current problem. I mean, it turns out that C++ has almost nothing to say about floating point arithmetic. It's very casual, really. And the reason for this is that not every implementation platform is actually IEEE 754 compliant. It's a hardware specification as well. And if the standard started mandating compliance with IEEE 754, with 60559, then suddenly we would have a whole section of implementations that were no longer compliant with ISO/IEC 14882, which is the C++ standard. What to do? Well, oh, no, we have to go back to the C++ standard comes to the rescue. What to do? Okay, this is a less sarcastic heading. C is also designed for platforms without IEEE 754 compliance. There's nothing mandating floating point behavior. However, there are some annexes to the C standard which help us out. More than half of the references to 60559 in the C standard are actually in these annexes. And the index, let's take a quick look. there are only 7 clauses in the C standard. 1 clause on language, 1 clause on library, and a bunch of other stuff, whereas C++ has 33 clauses. ISO drafting regulations have nothing to say about clause length. Does everyone know that we only just published C++ 23? We only just published C++ 23. We finished it February last year. It took a while to get published. I'm not going to tell you why on camera. Herb's here tomorrow, apropos of nothing. Anyway. Yeah, Annex F spins through ISO IEC 60559 in much the same way that I described it earlier. And C23 defines a macro called this. If an implementation defines this with the value 2023.11, that means that the implementation conforms to the specifications in this annex for binary floating point arithmetic. Okay, so yep, we're good to go. I assume it was adopted last November. And there's a corresponding macro for decimal floating point arithmetic. Not something we deal with in C++, but something which C does tell you how to support, even if you don't want to. And it then goes on, the annex goes on to cover a lot of 60559. It provides mappings for names. So, for example, binary 32 in 60559 is named float in the C standard. Binary 128 is named long double. And sometimes symbols are used. For example, so there is a function in the 754 standard called compares signaling not greater, which is much more understandable as not x greater than y. Sometimes cases are changed. Next up becomes next up. And so it works its way through 60559, does some changes, just makes it more legible. You can't just say, apply everything in ISO IEC 60559, boom, there we are. You've got to actually spell it out, and you've got to modify it according to the prevailing standard and the drafting rules, for that matter. Annex F9 covers optimization. This section identifies code transformations that might subvert IEC 60559 specified behavior and others that do not. They really aren't trying to help me here, are they? In my notes, I've spelled behavior correctly, by the way. And there's statements about code removal and code motion and expression transformations like 1 times x equals x, trivial operations. The wording is quite careful not to provide a way for compilers to play fast and loose with the standard, but we'll come back to optimization in a moment. The rest of the annex looks at math.h and tgmath.h, naming the functions that I'm sure you're all familiar with. Annex G looks at complex arithmetic. Annex H looks at interchange and extended types beyond float double and long double. But wait, I hear you cry. But wait, I hear you cry. What about ISO IEC 60559 Clause 11 reproducible floating point results? I'm sure you were all thinking. What indeed? And I've got a hypothesis here. I need to speak to some C people. So one advantage of being chair of programming languages for the BSI is that I get access to a lot of documents, including the original C standard from 1989. Although reading it is somewhat taxing because it exists as a PDF of a printed document, which can't be searched. You don't know how lucky you are today, you really don't. But searching through C89, the year of publication, you can find a really quite relaxed specification for the operation of floating point behavior, including a footnote on page 14. The floating point model is intended to clarify the description of each floating point characteristic. It does not require the floating point arithmetic of the implementation to be identical. And as far as I can see, there's no reference to 754, which was published in 1985. And C99, which features the annexes I described, explicitly references 60559. But recall that the first revision wasn't until 2008, which is when that 11th clause came in. Now, C11 also references the 1989 standard. And C17 was now a correction of C11. And it's not until C23 that the new standard from IEEE in 2019 is referenced. And while there's some tightening of the wording, there's no mention of the reproducibility attribute. So maybe nobody thought about it. Recall that make unique was introduced in the C++ 14 standard, while make shared was introduced in the C++ 11 standard. We said, yeah, make shared, great, let's have this. And people said, where's make unique? And we went, oh, yeah, sorry. And we put it in 14. We're all fallible humans making the standard. All right, let's look at optimization. As far as I can see, fusion and reordering, so fusion of instructions, and reordering instructions are the two methods of optimization available to the compiler. Let's go back to that compiler explorer example. So the problem we have here, it's actually here. So here we're calling LLVM FMA 32. We're not calling FMA here. So this compiler says, yay, we can use FMA. This compiler says, no, we can't. So we get different results. So different compilers, different results. What's worse, though, with Clang, I've already got the compiler option selected. If we do this, we choose the Skylake. Well, now, our distance is 0.1. Our projection vector is negative 0.08. I'm sorry you can't see all this. And this won't be on the slides either. But you should try this yourself. Go to the link, try March Skylake, or just believe me. But it's the use of FMA that's been problematic. And when we introduce Skylake up here, I think it's here, isn't it? No, it's not. Yeah, it is. Oh, hang on, where is it? Yeah, it is, it's here. So you can see we've got the FMA is back, plus we've got all sorts of vectorization going on because we have more information about the architecture, and the compiler's being very clever there. So how do we overcome reordering and fusion? And there is an unpleasant answer, which is rewrite the code. So there's a semicolon everywhere. And as I said, that's deeply unergonomic. That's not very satisfying. And also, the compilers have optimization flags. So first we've got MSVC, which has the FP fast option. So that's an obvious choice for optimization, isn't it? Which optimization model will we use? We'll use the fast one, please. And the FP fast option allows the compiler to reorder, combines it. It can do anything. It'll be fast rather than accurate. Like AI, that's fast rather than accurate, isn't it? And it's certainly not going to help for reproducibility. FP precise is the default compiler behavior, so it preserves the source expression, ordering and rounding properties, and all this kind of stuff. The compiler doesn't perform algebraic transformations on floating point expressions unless it can guarantee the transformation produces a bitwise identical result. The difference in performance is quite staggering. We've seen a threefold increase in running times when testing our code at 6 impossible things between fast and precise. GCC, so we've got float store, which is don't store floating point variables in registers, inhibit all sorts of options. We've got no math erno. Who uses erno in here? Good. Nobody. Lovely. We've also got -F, unsafe math optimizations. These are great. Who says naming is hard? Really, come on, that's great. No trapping math, which compiles that, which assumes that there's nothing the user's going to want to see. So, just swallow it all up. And we have fast math again. And that sets no math or no unsafe math optimizations and no trapping math to true. Sets those up. So if we turn off all math optimizations, write single operations for expression, and write our own maths library, are we golden? No. I'm currently in communication with some core experts about this. Look out for an updated version of this talk. And I don't know about you, but one of the reasons I like using C++, as I said, it's operator overloading. You want to be able to build expressions that look like they've just come out of a textbook. It's readable, it's legible. If you've got 65 operations spread over 65 lines, no one's going to know what you're doing. It's going to be hard to debug and test. I started programming in assembly language in the 1980s. I had an awful time putting maths functions together. It was ghastly. Have I really got to go back to doing things one step at a time? There's got to be a better way, and I have some ideas. So improving reproducibility of non-integral values. And this is what we're doing as a first crack at the problem at 6 impossible things before breakfast. We have a geometry template library, which takes an arithmetic type as a parameter. And currently we're defaulting to float. It's working fine, but it's not deterministic. What we need is a type that can be taken as a template parameter, exhibits floating point-like properties, and is reasonably precise. We don't need to be math precise here. We just need to be game precise. So mathematical correctness is not that important compared to speed. So it needs to be as fast as possible. And right now we're making good progress. We expect to open source our library in the fullness of time, but can we do better? What about changing the standard? Who'd like that? Oh, good, good, good. But not David, it seems. Right. So introducing the class from the prior slide, that's not going to fly. It's extraordinarily specific insofar as it sets aside 60559 entirely. What we need is some way of preventing reordering. Now, one idea that's been floated internally to my employers is the idea of having fences around which instructions can't be reordered, like memory barriers. Very poor ergonomics again. They'd be needed throughout all your code. They would greatly reduce the legibility of the source. It's not really, I don't like that idea. An idea I had recently was a new attribute, reproducible, which would identify a function as being immune from floating point optimization. And this would also advertise to the linker that link time optimization is not available for this function. Better still, a function qualifier. But one problem with such a function is that it must not call any functions which might affect its reproducibility. And that's quite a complicated bit of analysis that needs to be performed at compile time. The same problem arises with the idea of pure functions. Anyone familiar with pure functions? Pure functions are great. You call a pure function, you always get the same result back. It's completely self-contained. It doesn't depend on any outside information beyond the parameters that passed in. Eminently threadable, as I'm sure you can appreciate. This was proposed by Carl-Étienne Perron in September 2015 in P0078. You can tell it's old. It seems to have been dropped by the author. But if you've been paying close attention to the standardization of C, you'll know about paper N2956 unsequenced functions, which introduces pure functions via attribute to C. So we've now got pure functions in C23. But it also snags the word reproducible, so we need something else. In this month's mailing, I included this paper, P3375, reproducible floating point results. If you go to wg21.link/P3375, you can read it. God help you. It's pretty simple. I define this enumeration and this class. And the class defines operations, but it specifies that execution behavior of operations on objects of type strict float shall preserve the literal meaning of the source code. Operations shall not be reordered or fused. But I imagine that wording is going to need a lot of work. But I don't know about you, but whenever I ask a question on the internet, I immediately reply with the wrong answer from another account, and people swarm to it to write the correct answer. So I figure if I put this wording in, people will swarm there to provide corrected wording. I live in hope. Actually, I live in Hove, which is near Brighton. There is another paper in the same sort of space. Oh, hello. This one. Deprecate and replace FM rounding modes, which deprecates these two functions. Does anyone call FE set round and FE get round at all, day to day? So deprecation wouldn't hurt. That's nice to know. And it replaces it with a struct called rounded to represent the rounding mode. There are typical floating point operations on the struct, or in the struct, add, sub, mul, div, FMA, square root, and they're defined as binary functions, which are all carried out with the rounding mode passed to the constructor of that type. Neither of these papers are near complete. We're going to be talking about them next week in Wrocław, and I can't wait. I think it's going to be a really fun week for people like me. This doesn't look great for C++ 26, but, 29, maybe. There's always C++ 29. So this is where we are at the moment. I showed you how humans and digital machines deal with non-integral values. Then we looked at how this has been standardized, how we incorporated that into our standard. And finally, I wondered how we can improve on this, taking us towards portable floating point calculations. Thank you. Ask me 2 questions. Do we have a mic? We do have a microphone. Excellent. Who's first?
Hi. Thank you for the interesting talk.
You're welcome.
Do you know maybe, is there any language that makes it properly, like that
Yep.
standardized properly?
So, as I say, I was the... Oh, hello. Yes, as I say, I'm the chair of BSIIST 5, programming languages. And so the first thing I did when I wrote my paper was say, well, all right, let's see how the other languages do. So we have Ada, Fortran, COBOL, Prolog. Yes, Prolog. And again, in my position, I have access to all the standards. So I read them. those standards in the other languages, they're tiny, tiny things compared to the majestic 2,200 pages that C++ consumes. Fortran and COBOL, they specify all the way through, all of the operations should be carried out in accordance with 60559. Ada has its own floating point type, but it assumes that at some point in the future, it doesn't say how near that future might be, but it assumes that Ada will probably migrate to a 60559 type if there is enough interest in the continued usage of Ada. But no, as far as I'm aware, I don't believe there is a language that professes to be entirely and wholly compatible with 754, right down to reproducibility.
Okay, but I don't know. So follow up. So when those languages like Fortran and do it better, but they limit then the speed, for example. Yes.
Yep.
If you that's the trade-off. Yes.
The trade-off for reproducibility is eliminating optimizations. All of the optimizations make things happen faster, but at the cost of precision.
Okay. Thank you very much.
Uh-huh.
So I just want to double check. I mean, it sounds like you don't actually want to mandate that this is required, because as you noted, I think you said there was a 3x performance difference in some cases, and presumably, like, you want those optimizations in some cases.
So, yes. Now, so we have an attribute here. So the attribute means, all right, switch on this attribute for this region of code. So with struct rounded as being, the idea is that rather than using your regular arithmetic, you'd use the arithmetic provided on the struct. And that would do everything using that rounding mode. And in the same way, you could propose a struct called reproducible and do the same things that way.
Actually, one more question.
Okay. So it is a choice. It is an active choice to say, yes, I want reproducibility, and I'm prepared to pay the price.
So I guess as a follow-up to that, what about the library functions, right? So there's currently no requirements on like sine and cosine, and oftentimes like computing, especially the unit of last precision, like is extremely expensive.
Yes,
for
it is.
Values.
Yep. Again, we would not be able to specify trig functions that were reproducible, because to do so, we would have to specify an algorithm. The standard does not specify implementation, it specifies interface. So I would expect, so what we're doing in Six Impossible Things, we're not just writing our own geometry library, we're writing all our own trig functions as well, so that they are the same across the platforms.
Are you going to propose that for standardization?
Maybe. Probably not, though.
Not right away.
Not right away. We can't even walk yet. In fact, we're barely blinking in the daylight here when it comes to, we've got the extended floating point types. That's a great start. That's clause 3 of 11. We need to work our way through and decide which of these clauses are we going to conform with. To be conform with IEEE 754, it doesn't mean everything's in there, because there are some clauses that you should, or you may conform with, rather than that you must. Or the wording might, or there might be different wording, but some clauses are optional, like reproducibility is optional. The reproducibility clause starts with, if you want reproducibility, you should do this. And then tells you, right, which means you must do all of these things, but all of those musts are contingent on you actually deciding to support reproducibility in the first place. It is optional, but I'd like to add the option of reproducibility to the standard.
So if you have a type that is reproducible, like a reproducible float, you will still have a float as well. So you have to choose for each of your floating points whether you want the reproducible one and the non-reproducible one based on speed. In a game, will you sometimes use either or always use the reproducible one?
I didn't say it was going to be easy. What I would envisage is that you have your simulation as a library with inputs with inputs and interrogations, sets and gets if you want, and you'd write your simulation entirely using the reproducible floating point stuff. Your renderer, obviously, you want everything turned up to 11 for the renderer. Where you need reproducibility, you use reproducibility, you pay the performance penalty. Okay, so even once it's in there, people might decide, my simulation is massive. I can't. It takes up a third of my frame time. If I go take the reproducibility route, it'll take up all my frame time. We're not doing this.
Okay, thank you.
Thanks for the talk.
You're welcome.
One question. If we, for example, have fuse multiply add in all of our target
Mhm.
hardware, then could we also say, yeah, we want to have this FMA optimization also still enabled in the reproducible one, because every of those hardware has it?
You absolutely could, but you probably need to make it explicit. So rather than have the compiler infer, oh, I can see A times B plus C, I'll exchange that with an FMA, you'd actually use an FMA function. You'd say, I don't want that. I want an FMA here, and then have the compiler, do the work.
Thank you.
With the caveat, obviously, that FMA is not as clear as A times B plus C.
Yeah, so this question isn't about the portable stuff, but in your example of the graphics card that was changing attributes and not changing them back, is that something that is global to the hardware, or like the process? Like, do you have any power to change it back in your code, or is that something?
Oh yeah, I mean, it's what we ended up doing. We as soon as we came out of third-party code, we'd check all of the check what our attributes were.
And that will, like, if another thread, like, imagine you have like other threads not under your control in the process, like a plugin environment. Can you count on that working in your code? Or I don't know if that's like global to the process.
Floating point
or
environments.
the hardware.
Floating point environments are thread specific.
Yeah, that's what I was hoping.
Yep.
My code is doing that as
Oh,
well.
otherwise the buildings would be falling down around our ankles. Really, it would be awful. We'd probably have tidal waves and natural disasters befalling the northeast coast of the continent. Anyone else for questions, or shall I just ramble on for another 2 minutes?
Maybe you can show the page with the offer for your book.
Oh, the offer for my book. Oh, wow. I absolutely can. It takes a while, doesn't it? Of course, the wise lemming would probably click on the slide thing and then but I reckon I can get there faster this way. Or can I? It's a long presentation, isn't it? Oh, there we are. Oh, wow. Now that's more like it. Thank you. Yes. Yeah. I'm too shy. It's sold quite well. I'm quite pleased. I have another one coming at the moment, which is the Game Developer's Guide to Learning C++. And I figure the more people I tell, the more likely that I will actually write it and finish it. There's nothing like an audience of expectation to get you to do a thing. Any other questions? Oh, one more. Roth.
So the Total War Rome example, you said that 2001. So on Windows, were you dealing with like x87 and then like SSE on? Was that a problem you had to deal with,
No, that would have been no. We no, we weren't. Next question. I think we're done. Yep, 5 o'clock on my machine. Thank you all very much for coming.